Hi, my name is Divya Das and this is For the Love of Physics. In today's video, I want to talk about a very famous experiment of muon decay that ultimately provided experimental verification to the consequences of special theory of relativity, namely time dilation and length contraction. In my previous videos, I have talked about time dilation and length contraction. Whenever objects are traveling at very high speeds comparable to the speed of light, then the clocks associated with those objects tend to tick slowly compared to an observer at rest, and the meter rods associated with those objects appear to be contracted compared to an observer in rest. These very non-commonsensical and bizarre consequences of special theory of relativity needs to be experimentally verified for people to accept. Right. So here is one of those very famous experiments that provided an explanation as to how the consequences of special relativity come into effect. So let me explain the experiment to you. Whenever high energetic cosmic rays strike the upper atmosphere of the Earth, they end up creating subatomic particles like muons or mu-mesons. So these muons are subatomic particles that have a very short lifespan, and they eventually decay and lead to the creation of electrons or positrons and neutrinos, particles like that. However, some of these muon particles eventually reach the Earth's surface, and in this particular process, the amount of time that they take as they travel through the atmosphere provides us with an opportunity to study time dilation or length contraction, because the velocities at which muons travel is very high. They travel at nearly 98 to 99% the speed of light. So the velocity at which a muon travels is around 0.98 c. These are velocities where relativistic effects come into play. Now, before we talk about the relativistic effects, let me do a couple of calculations from a non-relativistic perspective so that you understand where the discrepancy lies. Now, to perform the non-relativistic calculations, first of all, we need to know a few things. First, I have already provided the velocity of the muon as it travels through the Earth's atmosphere along the vertical axis is 98% the speed of light, which is 0.98 c. Now, muons, as I said, are short-lived subatomic particles. They have an average lifespan, which I'm going to call as tau naught, of equal to 2.25 microseconds. 1 microsecond is equal to 10 to the power minus 6 seconds. Now, as the muons are created in the upper layer of the atmosphere and as they travel downwards, they travel a distance of around 10 kilometers. The distance I am referring to as d naught. Time taken t is equal to distance upon velocity. What is the distance? 10 kilometers or 10 to the power 4 meters divided by velocity, which is 0.98 c. So 0.98 into c is what? C is the speed of light, which is nothing but 3 into 10 to the power 8 meters per second. This is quite simply equal to 10 to the power minus 4 upon 2.94, which is equal to 34 microseconds. This is equal to 34 into 10 to the power minus 6 seconds. So this is the time that it takes for the muon to complete this journey of 10 kilometers as it is traveling with a velocity of 98% the speed of light. However, as I just now told you, these muons are radioactive particles. They have a very short lifespan, and within that lifespan, they decay into further subatomic particles like electrons, positrons, and neutrinos. Hence, whenever you are dealing with radioactive particles, then you usually look at the number of particles existing initially and the number of particles that existed later on. So, for example, what we can do is we can look at the flux of the muon particles at a particular height. So we can calculate the number of muon particles per unit area per unit time, and then we can calculate the number of muon particles existing at the sea level per unit area per unit time. Their relationship comes from the usual radioactive decay law. The radioactive decay law tells us that the number of radioactive particles, like the muons here, at any given point in time is equal to the number of particles initially at time t is equal to 0, epsilon to the power minus lambda t. T is the time that has elapsed and lambda is the decay constant. How is the decay constant related to the average lifespan? The decay constant is a reciprocal of the average lifespan. This is something that you must have studied when you are studying radioactive decay law. So this comes out to be n naught e to the power minus t upon tau naught. So the average lifespan is a reciprocal of the decay constant of any kind of a radioactive particle. Now in these calculations, you can use either the half-life or the decay constant or the average lifespan that I have used, but all of them will end up giving you the same results. I am using the average lifespan, so the radioactive decay law simply becomes like that. Now, I can compare what is the ratio of the number of muons at a particular height to that of the number of particles at the ground level of the earth or sea level of the earth by looking at the ratio of Nt upon N0. This is the ratio of the number of muons at the sea level to the number of muons at a particular height. And this basically gives us this particular number, which is e to the power minus t upon tau naught. Now, based on our quantities, the time taken for the muon to travel this particular distance of 10 kilometers is 34 microseconds, which becomes e to the power minus 34 divided by tau naught, which is the average lifespan, that is 2.25 microseconds. This becomes 2.25. If I solve this, this simply becomes e to the power minus 34 upon 2.25, which comes out to be around 15.1, and e to the power minus 15.1 comes out to be 0.27 into 10 to the power minus 6. So the ratio of Nt upon N0 comes out to be 0.27 into 10 to the power minus 6. So which gives us an idea about the number of muons at a particular height to the number of muons at the sea level. So this ratio is actually equal to 0.27 upon 10 to the power 6, which is 1 million. So if there are 1 million muons at a particular height of 10 kilometers, then according to our calculations, there should be 0.27 muons at the sea level, which is actually even less than 1. So that means you will need more than 1 million muons at a particular height of 10 kilometers for there to be at least 1 muon at the sea level. All of these calculations seems simple enough, right? However, there is a twist, and the twist is that the experimentally calculated flux of muons is very, very different compared to this theoretically predicted number. Experimentally, the amount of muons which are observed at the sea level is much higher compared to this number that is theoretically predicted if we do not take into account special relativity. The only way the experimental number, which is much higher than 0.27 out of 1 million muons, can be understood if we take into consideration the postulates of special theory of relativity, which predict that whenever objects are traveling at very high velocities, the times that they experience according to an observer in rest and the distance that they experience according to themselves are very much different. So there are two ways to look at the effects of relativity that are happening here. One is with respect to an observer at rest on the ground, and one is with respect to an observer that is on top of the muon. So let me discuss both of these one by one. So we are going to look at the relativistic effects now. So the first is when we look at this particular phenomena happening with respect to an observer on the ground. With respect to an observer on the ground, let's suppose there is an observer here who is looking at this particular phenomena. With respect to him, what is going to happen is actually time dilation. Let me explain what that means. You see, in relativity, every observer has a clock associated with it. And the rate at which these clocks tick, or the rate at which time flows, depends upon with respect to which observer the measurements are being made. So for example, in this experiment, the phenomena of a muon going from the upper atmosphere to the sea level is being measured with respect to an observer on Earth. So according to an observer on Earth, let's suppose that he has a clock associated with himself, and the clock is at a particular configuration when the muons is created at the upper layer of the atmosphere. However, according to him, when the muon reaches the sea level, his own clock will have proceeded further to a different configuration, whereas the clock of the muon will not have proceeded to that configuration, but rather the time period according to the muons clock with respect to this observer would be much lesser. This is known as time dilation. That means according to an observer on the ground, a moving muon's time flows slowly. That means the time of a moving muon is dilated, which means what? It means that the average lifespan is now not the same anymore for a moving muon. You see, the average lifespan that was calculated to be 2.25 microseconds is actually calculated in the rest frame of a muon. In a laboratory setup where the muon is at rest, in that kind of a setup, the average lifespan is 2.25 microseconds. But now, when the muon is traveling at a very high speed of 98% the speed of light, the average lifespan according to an observer in the lab is not the same anymore, because the muon's clock is dilated because of its relativistic speeds. The clocks associated with the muon are ticking slowly compared to an observer on the ground. And now we have to calculate what is the time corresponding to this average lifespan for a moving muon. So if a muon is traveling at a speed of v is equal to 98% the speed of light, in that kind of a situation, the dilated time, let's suppose it is tau, is equal to the time period measured in the rest frame of reference, which is 2.25 microseconds, divided by root over 1 minus v square upon c square. So if a muon has an average lifespan of 2.25 microseconds for an observer in rest, the same muon traveling at a speed of 98% the speed of light will have an average lifespan of tau is equal to tau naught upon root over 1 minus v square upon c square, which is what? So tau naught is equal to 2.25 microseconds divided by root over 1 minus v is 0.98, so this becomes 0.98 square. So this is nothing but 2.25 microseconds divided by root over 1 minus 0.98 square is somewhere around 0.96, which comes out to be 2.25 microseconds divided by root over 0.04, which comes out to be 2.25 microseconds divided by 0.2, which comes out to be somewhere around 11.25 microseconds. So that means if a muon at rest has an average lifespan of 2.25 microseconds, a muon moving at a speed of 98% the speed of light has an average lifespan of 11.25 microseconds, because the time associated with the moving muon is dilated. And now we can perform the same calculation of the ratio for tau is equal to 11.25 microseconds. So if we look at the ratio now, nt upon n naught comes out to be how much? It comes out to be e to the power minus t upon tau, where tau is 11.25 microseconds. So t is 34. So e to the power minus 34 upon 11.25. This ratio minus 34 upon 11.25 comes out to be 3.02. So this becomes e to the power minus 3.02. So e to the power minus 3.02 comes out to be 0.0488. 0.0488, which is what? This is actually equal to 0.0488 is equal to 48800 upon a million. 48,800 upon 1 million. Which means what? It means that 48,800 muons out of 1 million muons will survive as it travels through the atmosphere. So that means if there are 1 million muons created at the upper atmosphere, out of them 48,800 muons will reach the sea level, which is very much different from the earlier number that we observed. The earlier number was out of 1 million muons, 0.27 muons are supposed to reach the sea level according to non-relativistic calculations. But the moment we take time dilation into account, this ratio is much closer to the experimentally observed ratio, which provided validation as to the idea of the time dilation. You see, for an observer on the ground, the clocks associated with the muons tick slowly. The time period of the muons is dilated, because of which the average lifespan measured in the rest frame of reference is not the same as the average lifespan measured for a moving muon, which is 11.25 microseconds. And according to this number, a larger number of muons should reach the sea level, because the lifespan of a moving muon suddenly increased compared to its lifespan in the rest frame of reference. So this is the calculation of the number of muons, or the ratio of the muons that should survive the sea level, that very well matched with the experimental data, thus providing a kind of an experimental verification to the idea of time dilation. Now, we can look at this calculation from the perspective of another observer. Which is that observer? That observer is muon. You see, first we did the calculation with respect to an observer on the ground. But what if we looked at the phenomena with respect to an observer that is standing on top of the muon? So let's suppose that there is an observer which is sitting on top of the muon. How does the entire phenomena look according to him? So let's look at that also. So with respect to an observer on the muon, if there is an observer sitting on top of the muon, with respect to that observer, what you will end up see is length contraction. Why? Because according to an observer on top of the muon, his calculation of the rest lifespan of the muon is still 2.25, right? His calculation does not yield a lifespan of 11.25, because according to him, the muon is at rest. According to him, only the earth is moving. According to an observer on top of the muon, it is the earth's surface that is traveling rapidly towards him with a velocity of 98% the speed of light. According to him, the muon still decays after a lifespan of 2.25 microseconds. So if he agrees on the lifespan of the muon, what changes according to him? According to him, what changes is the distance that he has to travel. The distance that he has to travel is not 10 kilometers anymore, but rather it is contracted. So with respect to an observer sitting on top of the muon, the lifespan of the muon is still the same, that is the laboratory lifespan of 2.25 microseconds, but the distance is now contracted. So if you look at the contracted distance v, that comes from length contraction, which is 1 minus v square upon c square into d naught. What was d naught? That was 10 kilometers, right? And what is 1 minus v square upon c square? That is 0.98 square, and d naught was 10 kilometers, so 10 to the power 4 meters. So this comes out to be how much? This is 1 minus 0.96 into 10 to the power 4 meters. So this comes out to be 0.04 into 10 to the power 4 meters. So this comes out to be 0.2 into 10 to the power 4 meters, so which comes out to be 2 kilometers. So now, according to the muon, the distance of the entire vertical direction of the atmosphere is contracted. So according to the muon, he does not have to travel a distance of 10 kilometers, rather he has to travel a contracted distance of 2 kilometers only. So what is the time required for the earth as it's traveling towards the muon with a velocity of 98% the speed of light? With respect to an observer on top of the muon, what is the time taken? T dash is simply equal to distance divided by velocity. So distance is 2 into 10 to the power 3 divided by the speed at which the earth is approaching the muon, which is 0.98 into 3 into 10 to the power 8. This comes out to be around 6.8 microseconds. Alright, so the time it takes for the earth surface to reach the muon as it is traveling with a velocity of 98% the speed of light, because that is how the observer on top of the muon will see things, right? So the time it takes is now 6.8 microseconds. So this is the time it takes for the earth to cover the contracted distance of 2 kilometers according to an observer on top of the muon. So now, if you calculate the ratio of the number of muons on the sea level with respect to the number of muons on the upper layer of the atmosphere is equal to e to the power minus t dash upon tau naught. T dash is the time it takes for the Earth's surface to travel from here to here, and tau naught is the average lifespan compared to an observer at rest with respect to the muon. So this is simply equal to e to the power minus 6.8 microseconds upon 2.25 microseconds, which gives us a number of e to the power minus 3.02, which gives us a number of around 0.0488, which means this is equal to 48,800 upon 1 million. So if there are 1 million muons created on the upper layer of the atmosphere, 48,800 of them will reach the sea level. So if we perform the calculations taking into account length contraction with respect to an observer on top of the muon, I end up getting the same results that I got previously when I did the calculations with respect to an observer on the ground, where I took time dilation into account. So this experiment therefore provided an experimental verification to the ideas of time dilation as well as length contraction, because it yielded results which were matching the experimental observations, and the usual non-relativistic calculations could not explain the experimental observations. Thus, time dilation or length contraction provided a reasonable prediction to the experimental observations of the change in flux of muon decay as it is traveling through the Earth's atmosphere. However, you cannot apply both these phenomena simultaneously. You need to take into consideration with respect to which observer you are making the calculations. Are you making the calculations with respect to an observer on the ground? In that case, he will observe the time to dilate for a particular muon. So therefore, you take time dilation into account. Or are you performing the observations with respect to an observer on top of the muon? Because for him, the length will get contracted. Are you seeing? It depends with respect to which observer you are doing the calculations. With respect to an observer on the ground, the muon's time gets dilated. With respect to an observer on top of the muon, the Earth's distance gets contracted. So either you apply time dilation with respect to an observer on the ground, or you apply length contraction with respect to an observer on top of the muon, but in both the situations, you will end up getting the same results, which matches with the experimental data of this kind of a muon decay. So this is one of those experiments which yielded an experimental verification to the theory of relativity. So that is all for today. I hope you learned something from it and you enjoyed the video. That is it for today. Thank you very much. I'll see you in the next one.